Today we are working on lesson 4.5. Our topic is simplifying radicals. Okay, before we get to the new content, let's do some bell work. They've asked us to multiply polynomials, so we'll take some time to do that. If you feel confident with this topic, go ahead and pause to work them out and then check your work afterwards. Okay, so 1 and 2, I directly applied foiling. Number 3, you need to be super careful with. You have a quantity squared, which means you're supposed to take a x minus 7 times itself in parentheses, and then FOIL. So rewrite first, then FOIL. As you notice, we're always looking for those middle terms to be our like terms. Sometimes they cancel out, but sometimes they do not. Like this situation, negative 7x minus 7x is minus 14x. Recopy the plus 49. And then on this next one, we are just distributing. So that is an x to the first. Remember, when we multiply a variable with the same base, we add the exponents. That makes 3x cubed plus 15x squared. All right, now for our new content. As I mentioned, we're working on simplifying radicals. So let's take a look at this information in the box together. Different properties of our radicals. We're working on square roots. The square roots of a product equals the product of the square roots of the factors. That sounds kind of wordy. So let's take a look at this. They are assuming that whatever information A and B is representing is something positive. Is what that A is greater than 0 and B is greater than 0 is implying. A and B are both positive. So A is a positive number. B is a positive number. That is what that is really saying. So here we are. We have the product of AB under the radical. Just be aware that that is the same thing as if you have the square root of A times the square root of B. So an actual example is to the right of that. The square root of 4x is the same thing as if we took individually the square root of 4 times the square root of x. The reason why we'd want to do that is because the square root of 4 is perfect, and it has the simplified answer of 2. Square root of x does not break down any further, so you keep that as square root of x. Same thing happens with division. We have a divided by b under the radical. You can take the square root of the numerator, which is a, over the square root of the denominator, which is going to have b under the radical. So a particular example is the square root of the fraction 2/25. So again, separately, take the square root of the numerator, so square root of 2, over the square root of the denominator, which is square root of 25. Square root of 25 happens to be perfect. That's why you see 5 written without a denominator. Without a radical symbol in that denominator, whereas radical 2 is in its simplest form, so you have to keep it radical 2. So we've got these rules next for radical expression in simplest form. So things becomes like your checklist. No perfect square factors other than 1 in the radicand. No fractions in the radicand, and no radicals appear in the denominator of a fraction. Okay, so we'll do some examples so that this all becomes clear. So on the left side, we have examples of perfect squares. So the square root of 25, there's a couple ways you can think about this. I could rewrite 25 as 5 squared. And so the square root of 5 squared is just 5. The square root of 144, you could think of that as square root of 12 squared, which then would give us just 12. Okay. So final answers on each of those. Square root of 25 is 5. Square root of 144 is 12. And you just might know that directly, and that is totally fine. Now, on these non-perfect squares, what your job is to do is to look for perfect square factors. So you need, and I'm going to add a page here real quick. So make sure there's nothing there. Yep. What I highly recommend is getting a piece of paper, and you are going to write down perfect square numbers. Okay, and so we start off with let's start off with 1 squared. 1 squared is 1. 2 squared is 4. And I want you to keep going all the way to 15 squared. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared, we have 100. 11 squared, we end up with 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. Kind of pause for a moment here. 169 versus 196. Notice those last 2 digits are just switched. But I know 14 squared has to be bigger, so that's how I kind of remember 14 squared is 196. And then, of course, 15 squared is 225. So I'm having you write these down because these numbers are popular. They will show up in problems working with radicals, working with square roots, and solving equations as well. So it's going to just be helpful to have this in front of you. It'll help you think about perfect factors when we're simplifying. So like I said, it's probably best if you have it on a separate piece of paper so you can have it side by side with your laptop and your homework while you're working on these, as well as our notes that we're doing right now. So back to our non-perfect squares, that yellow side of this page of notes. Radical 12, what I'm looking for is what times what is 12, and one of those factors has to be on my perfect list. So let me backtrack then. On this one, what we would be looking at. So we want to find the biggest number that goes into 12. That is going to end up being the number 4. So we will have square root of 4 times square root of 3. Well, the nice thing about the square root of 4 is it's perfect. We know the square root of 4 is 2, and then we keep 3 under the radical because it's not perfect. Now with 48 under the radical, notice 48 divided by 4 is 12. Okay, the problem here is 12 is not simplified completely. So we could do radical 4 times radical 12, but there's actually going to be larger perfect factor that can help us, namely 16. So if you double check and take 48 divided by 16, you end up getting 3. So that means we would have radical 16 times radical 3. This is the best option because if you purposely pick the biggest perfect factor, that means less simplifying work for yourself. So for radical 48, we are going to use square root of 16 times square root of 3. Square root of 16 is perfect, which is 4. Radical 3 is not perfect, so that stays under the radical. So 4 radical 3. Okay, so let's try some more. Now we have a little bit of mixture here. This next one is a square root of 36x squared on here. So you can take a look at this as the square root of 36 times the square root of x squared, 36. And as you look back at our list, that is on the perfect list. So square root of 36 is 6. Square root of x squared is going to be x. And in the middle, we have square root of 25 over square root of 4. Both of those are perfect. So this simplifies down to 5 over 2. So again, if you need to, you go back to that list. Notice there was the 25 and there was the 4 from our list. And over here, it's just variables, but this is going to be like how we dealt with x squared under the radical in that first one on the left. So I would separate square root of a squared over square root of b squared, and that is a over b for our answer. Okay, here's some more scenarios. Again, we're going to separate the numerator, square root of 45x squared over square root of 5. So we have several things taking place here. And actually, I'm going to backtrack. I need to show you something else here. On this particular problem, pay attention to the numbers first. So I got a little bit of a tunnel vision there for a moment. Look at 45 and look at 5 under that radical. Are those divisible? I'm hoping you're telling me, yes, Mrs. Jones, they are. So what we're going to do is simplify under that radical first. 5 goes into itself once, and into 45 9 times. So we're really left with the square root of 9x squared. And I can look at that as the square root of 9 times the square root of x squared. Both of those are perfect, so our answer is 3x. All right, the middle example, 45. So take a look. 45 is not on this list. Okay, and I'm just kind of draw your attention right here. We've got 45. That would be a number between 36 and 49. So I need to look at the smaller numbers, 36, 25, 16, 9, 4, and 1, and figure out what's the biggest one that goes into 45 evenly. And that would be the number 9. So that gives us what, 5? So that would mean square root of 9 times square root of 5 represents square root of 45. Okay, and square root of 9 is perfect. That's why we choose that. And then radical 5 is totally simplified, so it stays under the radical. All right, then our next one, we have square root of 4x. So separate square root of 4, square root of x. Square root of 4 is on our list. That's perfect. And notice that is an x to the first. So it's not a squared piece of information, so that needs to stay under the radical. So 2 square root of x. Okay, our next series of problems, this next one is multiplying. What you're going to do here is multiply the coefficients together, and then you're going to multiply the radical pieces together. So 2 times 6 is 12, and radical 5 times radical 6 makes radical 30. On our next one, this is a situation where we were adding radical terms together, and it is legal to add these together because they are technically like terms. Both terms have radical 5. So that is like similar to like if I had 7m plus 10m. Those are like terms because they both have an m to the first in them, and that would give me 17m. So in this particular situation, radical 5 is like the m. And so I'm going to take 7 plus 4, and we're going to get 11, and keep the radical 5. So that is what combining like terms looks like, working with the same radical piece. All right, so we've got another special situation to work with. It says restrictions with square roots or the radicals. You cannot take the square root of a negative number. At least we're not presenting you how to do that yet. That is going to be later on in Algebra 2. So right now we are only dealing with positive values under the radical. There's another rule that we have to follow. We cannot have a radical left in the denominator of a fraction. So we have a process that we will go through to help fix that if you do end up or are presented with a fraction with a radical in its denominator. All right, so here's a couple of examples. Square root of 2/5, and then the other one is 3 over 7 plus radical 2. We have to go through a process called rationalize the denominator, which means we will be multiplying by a form of 1 on here. So that doesn't mean a whole lot to you yet until we actually go through some examples. Okay, so before we do an entire problem, we need to show you a couple of situations and what happens when we multiply them together. So for instance, radical 3 times radical 3, it's the same piece of information. That technically means square root of 9, which is perfect and gives us back 3. Radical 10 times radical 10, well, that would make square root of 100 underneath. But if you go back to our perfect numbers list, 100 is on that list. Our answer is 10. Therefore, if you kind of look at the pattern, if you take a radical value times itself, its answer is that number without the radical. It's how some people like to view this. So the same thing happened with the tens. Radical 10 times itself. Well, in the very end, the final answer is just 10. So it's that quantity without the radical. So that would lead you to believe then if we take the square root of x times the square root of x again, technically that makes the square root of x squared, but once we simplify, our answer is x. So when you multiply a radical piece of information times itself, the radical, in a sense, they undo each other. It creates that perfect situation to help you simplify. All right, so here's another situation. Working with the ratios. So we're going to work on our rationalizing technique now. So first thing, take the fraction and separate this into the radical of the numerator over the radical of the denominator. Then we're going to end up multiplying by a quantity of 1. This is what we call rationalizing the denominator. So you look and see what is in the denominator, and you use that as your multiplier. And I just make sure in my ratio that's in red, I use it in the numerator as well as the denominator, because technically this means the number 1. And if you multiply 1 by anything, you don't change the value on there. And that's why we're doing it this way. Now, it does create a cosmetic change, meaning things look different. But because we definitely know we're only multiplying by 1, they have to be equivalent. So go across the numerators. Radical 2 times radical 5, that is radical 10. Go across the denominators. Radical 5 times radical 5. Now, technically, that's radical 25. But that is a perfect number, and its final answer is 5 down there in the denominator. So let me pause for a minute. That denominator procedure, when you take a radical value times itself, that same quantity, then that number ends up being the final simplified answer. So that is what we had done right beforehand to show you that particular pattern that you could use. So the final answer of simplifying radical 2 over 5 is radical 10 over 5. So let me write this down. I said it, but I feel like it needs to be written down in words. What is in red is called rationalizing the denominator. Okay, let's try this again with a new problem. On this next one, they were nice. They already have the fractions separated. So radical 3 over radical 8. Okay, so we're going to, our first step be to rationalize. So you just look at what is in the denominator, and that tells you exactly what you want to use. So radical 8 over radical 8. Okay, now we'll multiply across the numerator. Radical 3 times radical 8 makes radical 24. And radical 8 times radical 8 is technically radical 64. This is where you could technically skip that step because radical 64 we know is 8. So if you are recognizing that pattern I just presented to you up above to jump down to the final simplified answer, that's totally fine. Now, you do have to be careful because our answer isn't completely 100% simplified yet. So what you need to do is consider square root of 24. That needs some work done on it. So as we continue this particular problem, we have to consider what is a perfect square factor of 24. What would be the biggest perfect square factor? So this is where I'd be going back to my list and considering, all right, which of these numbers goes into 24 evenly? And more specifically, what's the biggest number on that list that goes into 24 evenly? And for us, it is going to be the 4. So square root of 4 times what is 24? Square root of 4 times square root of 6. Okay, I know radical 4 is 2, so recopy radical 6, that's over 8. And then you get to simplify one more time. So those numbers that are not in a radical can simplify. 2 goes into itself once, and 2 goes into 8 4 times, meaning our final answer is square root of 6 over 4. So that's the one I'm going to box. But again, what I wrote in the red ink in both of these problems is representing, rationalizing the denominator for us. Okay, so this is rationalizing the denominator when you have a single fraction. There's no adding and there's no subtracting involved in either of those problems. But adding and subtracting can be part of what we have to deal with. So we're going to talk about that next. It says stop here because it wants you to pay attention. This situation is different from what we just did because of the adding, which could also sometimes be subtracting down there in that denominator. So take a look at what it says we're going to do. We're still rationalizing, but the specific process is called multiplying by the conjugate. Okay, and the conjugate will depend on what you have in your problem already. So if we have a plus radical b, then you will use a minus radical b as the conjugate expression. And likewise, if you start off with subtraction, then it would be adding for the conjugate expression. So this whole particular table is a good reminder of our scenarios and what we'll be using as our multiplying fraction, like what I wrote in red for those other problems, to help us rationalize. All right. So we introduced the word conjugate, but we haven't really done anything with that yet. So let's do a little bit of practicing. If the expression is 7 plus radical 2, and you're asked to multiply by its conjugate, the expression that is the conjugate is 7 minus radical 2. So it's the same thing, but is the opposite operation in between the middle of those terms. So likewise, 6 minus radical 3, the 6 and radical 3 are the same, but I'm using adding in between those terms. On this next example, the numbers involved are -5 and radical 5. The only operation that changes is the one in the middle. Okay, so notice I did not switch that first term to be a positive term. It stays exactly the way it is. So it's only the operation in the middle of the two terms that switches. Okay. All right, so it says what happens when you multiply an expression by its conjugate. So it says, let's see, if we multiply 4 plus radical 6 by its conjugate. So let's take a look. If I have 4 plus radical 6, that's the original, if I multiply it times its conjugate, the conjugate would be 4 minus radical 6. So that's what I'll put in my second set of parentheses. And then from here, you're going to FOIL. 4 times 4 is 16. Positive times negative is negative. That would be -4 radical 6. On the inside, we have positive times positive, so plus. It's radical 6 times 4, which I'll write down as 4 radical 6. And then positive times negative is negative. Square root of 6 times itself is just 6. And so what you should be noticing right now is that these middle terms are like terms, but they are also opposites. -4 radical 6, positive 4 radical 6. So those middle terms in the FOILing process are canceling out. We are left with 16 minus 6, which is just 10. Okay, so when you multiply conjugate expressions, something you can always count on is that the middle terms are going to be opposites and they will cancel out. That is the convenience of multiplying by a conjugate. Now, this next expression, these are not conjugate terms on here. So they just want to show you, they want to emphasize what happens when you multiply binomials that contain radicals as far as the answer goes. So I'm still going to work on FOILing. 1 times 7 is 7. Positive 1 times negative radical 6 would be negative radical 6. On the inside, positive times positive, so that's plus 7 radical 3. And then we have our last terms, positive times negative, so that's a minus. Square root of 3 times square root of 6 is square root of 18. I do and should take time to simplify. So right there, we're going to simplify. So what that means is radical 18, you need to find the perfect square number on our list that goes into 18. That would be 9. Radical 9 times radical 2. So once I simplify, that is 3 radical 2. So I will update my answer now. I have 7 minus square root of 6 plus 7 square root of 3 minus 3 radical 2. Okay, none of those terms are like terms. Nothing canceled out. So you need to just be aware. If you are multiplying and the terms are not conjugates, all the terms matter. If you are multiplying conjugate expressions together, then you can count on the middle terms canceling out. All right, I do believe we have a couple practice problems next. So here we go. First things first, it does flat out tell us, make sure you rationalize the denominators. We will be multiplying by the conjugate to get us started. So 3 over 7 plus radical 2. Well, I need the 7, I need the radical 2. The original operation's plus, so the conjugate expression's operation will be minus. Remember, I'm technically going to be multiplying by the idea or value of 1, so that is why the numerator gets the exact same expression. From here, I am going to be distributing the 3 in the numerator, so that is 21 minus 3 square root of 2, all over. Notice my use of parentheses that I'm using in this problem to help me correctly multiply. Down in that denominator, we FOIL. So 7 times 7 is 49. 7 times a negative 2 is negative 7 square root of 2. Then in the inside terms, we have positive times positive, so plus 7 radical 2. And then the last terms, positive times negative, so that's a negative. Radical 2 times itself is just 2. So we end up with, in the denominator, the middle terms cancel. And writing our final answer then, we have 21 minus 3 radical 2 all over. We have 49 minus 2, which is 47. I'm going to box that. That answer's done. All right. Last one, practicing this rationalizing the denominator procedure. Write down what it is you're multiplying by. So we have 6 and a radical 3. I look at the original operation subtraction. So this conjugate expression is 6 plus radical 3. Use that on the top and on the bottom. Okay, like we just did a moment ago, that negative 5 is going to be distributed to both terms in the numerator. So that is negative 30 minus 5 square root of 3. Down in the denominator, insert these parentheses to help you remember your process we want to use is to FOIL. So that would be 6 times 6, or 36. Then we have positive times positive, so plus 6 radical 3. Then we have negative times positive, so minus 6 radical 3. And then we have negative times a negative, so that's minus. Radical 3 times itself is just 3. And again, those middle terms are opposites, so those are now gone, and we can write down our final answer. We have negative 30 minus 5 square root of 3. That is all over 36 minus 3, which is 33. Okay. Now, with this particular problem, I'm going to box that as an answer, but I also want to show you there's a part of this problem that simplifies. If you take each piece and divide it by 33, notice what result would be for one of the fractions. There's a smidge more of simplifying that could take place. Okay, that negative 30 over 33, both of those are divisible by 3, giving us negative 10 over 11. And then that second fraction, the 5 and the 33, they don't simplify, so I'd have to leave them alone. So this would be another acceptable answer if you wanted to do some more simplifying. So that's why I said or there. I do believe we finished our last example, so you're ready to work on worksheet 4.5.